Okay, actually, I lied in the last video. I know I said we were going to Diffie-Hellman key exchange, and I know you were excited to get to that as well. But before we finish PRNGs altogether, let's talk about one more application called a stream cipher. So remember that when we talked about one-time pads, we said that one-time pads are secure as long as we never use the same pad twice. And just now we saw that PRNGs allow us to cheaply generate lots of random output. So what if we use that cheap PRNG output as the pad to a one-time pad? If we combine these two ideas, we get a symmetric encryption algorithm called a stream cipher, and it works something like this. This is a symmetric key scheme, so we're going to assume that Alice and Bob have a key that no one else knows. So what Alice will do to encrypt the message, she will seed the PRNG with her secret key. She will generate as many output bits as she needs. So if this is a really big file, she can generate 1 million pseudo-random bits, and the PRNG can do that. And we'll take the plain text, we'll XOR it with the PRNG output, and we'll get ciphertext just like in a one-time pad. Then we'll send the ciphertext over to Bob. And then Bob will do the exact same thing to generate the pad. He'll take the PRNG, seed it with the same key, and remember PRNGs are deterministic, so now when Bob asks to generate 1 million bits of PRNG output, he will get the exact same PRNG output as Alice did. He can XOR that PRNG output with the ciphertext and get the original plain text back. And if you are an eavesdropper like Eve, you don't know the secret key, so you are unable to generate the PRNG output, so you are unable to decrypt this message. So that's what a stream cipher looks like. One problem with our construction so far is that it doesn't allow us to encrypt multiple messages. If Alice now tries to encrypt a second message, she's using the same seed, so the PRNG will generate the same output, and she is reusing the pad in a one-time pad, and we know that is bad. So to fix this, we have to actually introduce an IV, and the resulting scheme looks something like this. When Alice wants to encrypt the message, she will first generate a random IV, and she will seed the PRNG with not just the key, but also the IV for this message. And only after that will she generate the random bits that she needs out of the PRNG, and then XOR those random bits with the plaintext to get ciphertext. And now, the ciphertext that Alice sends to Bob, it's the ciphertext from the one-time pad, but it's also the IV. So the IV also has to be sent to Bob. And now to decrypt, Bob takes the IV that he just received, it's a public value, and he seeds his PRNG with the secret key, which is the same every encryption, and the IV, which is special for just this encryption. That's the same seed as Alice used, so he will generate the same pseudo-random bits, and then he can use those bits to XOR with the ciphertext and get the original plaintext back. So to encrypt multiple messages, we have to introduce IVs, and remember to use a different IV for every message. This works just fine.